I'm just going to try and explain something which I've been thinking about. Oh dear, I was going to do this live stream and I decided against it because, yeah, I don't want to really do it live right now. Let me get my pointy thing. Hang on a minute. I'm just doing it on my phone. Now, I had this idea last night. The secondary coils are actually these in the middle, right? These are the secondary coils. Now, in the solid state device, these are my actuation coils, right? So these coils were pushing and pulling on the magnetic concentrics that are inside the red parts. These red parts are concentric magnet arrays, right? So when this coil is energized, it's actually retracting, say it's south on this side, it's actually subtracting on the north field on this side of the concentrics, right? So everything's flipped. Now, what I'm thinking about last night is about 4 years ago, I had some interesting effects where when I was putting a load on the secondary coils, the rotors actually speeded up, and I thought, well, that's interesting. And it turned out, figuring it all out, it was due to an imbalance in the system. I mean, at the time I had a lot of extra magnets, and I had a secondary concentric right in the middle, right? So I had another concentric that was unpowered right in the center, and the magnetic field was offsetting, it was shifting across, right? And it was due to that shift that it was creating a balance on the actual rotors, and the rotors were speeding up. Now, what's come to me, what I was thinking about last night before I fell asleep, was that by cross-connecting the actuator coils which are on the north-facing magnet on this side, this is north, right, say, and the other coil down below, these other set of coils at the bottom down, are actually facing a south-facing magnet, right? Now, normally what happens is you have a certain amount of drag because of the approach of the magnets and as the magnets just move away from the concentrics. Now, what would happen if we cross-connected the actuation coil on this side to self-power the actuation coil on this side, which is on the opposite side, through a capacitor coupling, and cross-connected the actuation coil on this side with the actuation coil on this side, right? Basically, that would cancel out the LENZ effect. So, you see, what's happening, right, is when we have a force, and an energetic force coming in onto these concentrics, there's a repulsion, or there's friction. Now, that power, if that was sent to the other concentric down here, that would aid this rotor on this side to actually gain speed. So basically, the resistance that we see on this side would be cancelled out by an equal pulling force on this side down here, right? And the same with this actuation coil on this side. When this coil is actually seeing resistance on the rotor, that power would be self-energized through to this side, and this coil also would be sending energy back to assist this coil. So they're actually pulling against each other all the time. They're also always assisting each other. That would cancel out the drag. Now, the only coils that we take power from are actually the internal coils. Now, as these coils increase on power, right, as these coils consume more power, the amount of drag will also increase, but these coils on the outside will register that extra amount of drag and will reinforce the rotor down on this side even more to counteract that drag. Okay. Right. I hope you understand what I'm talking about.